Settle in and let yourself grow heavy. There's nowhere to be now, nothing to do but rest. This evening, we'll drift slowly out toward Jupiter and its 4 ancient wandering moons. If these carry you off to sleep, subscribe. A new one comes every night. The cold came first, before the stars were named, before the tube was raised, before any eye had pressed itself against the glass. The cold was there, settling into the stones of Padua, the way it always had in January, the way it would have settled without anyone watching, without anyone alive to notice, the deep winter sky lying open and dark above the rooftops of the city. A man stood at a window, or perhaps he stood in a courtyard. The exact place has been softened by time, the precise posture lost, but the cold has not been lost, and the darkness has not been lost, and the long brass tube resting in his hands was real and heavy and slightly awkward, the way all new instruments are before the body learns to hold them. He steadied it. He pressed one end to his eye. The field of view was narrow and faintly curved at the edges, the way looking through a tube of water looks, everything slightly bowed, and in that narrow, imperfect circle of magnified sky, one bright point held steady in the east. Jupiter, a cream-colored point of light that had always been there, always moved slowly against the background of the fixed stars, always risen and set with the patient reliability of a body much larger and slower than it appeared. People had watched it for thousands of years. Shepherds, priests, navigators, the builders of stone circles who tracked its returns through the long dark of northern winters. None of them had seen it the way this man saw it now. The instrument in Galileo Galilei's hands in January of 1610 was not the first telescope made. Lenses had been ground in the Netherlands the year before, combined into arrangements that made distant objects appear closer. The device sold as a novelty, and then as a military curiosity, and then, in the hands of this particular man, in this particular winter, in a city on the plains of northern Italy, as a tool for looking at a sky that had never been properly looked at before. Galileo had refined the design himself. The magnification he had achieved was roughly 20 times. A hill 5 miles distant appeared as though it were a quarter of a mile away. The moon, seen through the tube, revealed a surface nothing like the smooth silver disk the eye assumed, and Jupiter, small and bright in the cold January dark, revealed something no one had thought to expect. There were stars near it, small ones, too faint to see without the glass, but not faint at all once the glass was between the eye and the sky. 3 of them, that first night, arranged in a nearly straight line so close to Jupiter that they lay almost against the planet's disk, 2 on one side, 1 on the other, all 3 aligned along an invisible band that ran east to west across the field of view. 3 small points, still, patient, there. Galileo wrote them down. The notebook was ordinary in the way all objects of great consequence are ordinary before their consequences understood. Paper, ink, a ruled page, a hand accustomed to writing that moved across the sheet in the careful small script of a man recording something he was not yet sure he understood. He drew Jupiter as a small circle. He drew the 3 points as asterisks, roughly positioned on either side. He noted the time, the conditions, the quality of the seeing, and then he went back inside, out of the cold, and let the night continue without him. The following night, the cold returned. The sky was clear. Galileo raised the tube again, found Jupiter in the eastern sky where it always was, and stopped. The 3 points were still there, but they had moved. Not moved the way background stars move, which is to say very slowly, imperceptibly from one night to the next, the whole vault of heaven rotating in its stately way as the earth turns. These 3 points had moved relative to Jupiter. They had changed their positions with respect to the planet, not with respect to each other and the background. 2 were on the same side now, 1 was on the other. The geometry was different, and something in the careful analytical mind that had spent years measuring pendulums and falling objects and the behavior of inclined planes recognized immediately that this was not the behavior of background stars. He watched again the next night and the night after. The points kept moving. They rearranged themselves. Sometimes all 3 were visible. Sometimes 1 or 2 disappeared behind the disk of Jupiter itself, or passed in front of it, and then reappeared. And by the 13th of January, not quite 2 weeks after the first observation, a 4th point appeared. Small, faint, clearly part of the same system. 4 bodies orbiting Jupiter, tracing paths around the planet, the way the moon traces its path around the Earth, completing their circuits in times that Galileo began to measure and predict. The orbit of the innermost body was shortest, a few days. The outermost took more than 2 weeks. All 4 moved in roughly the same plane, which is why they appeared strung out in a nearly straight line whenever Galileo looked, the geometry of an orbital system seen edge-on, compressed by perspective into a thread of light alongside the planet's bright disk. Galileo could predict from one night's position where each body would be the following night. He was right. He was right again and again. The nights continued to come, cold and clear and opening. In those pages of the notebook, ink drawings that looked to a modern eye like small maps of a simple and elegant system. There is something that takes a moment to settle into full significance. The drawings show position after position after position, each one dated, each one recorded, with the precision of a man who understood that precision was the only tool he had. The circles and the tiny marks beside them form a sequence, and the sequence is a discovery. Not a discovery made in a single flash, but one made slowly, incrementally, in the cold, in the dark, over weeks of patient watching. The discovery is not a thing, it is a motion, and the motion tells a story. The sky had been holding for 4 billion years before anyone was there to read it. Galileo named them the Medicean stars, after the powerful Medici family of Florence, whose patronage he was seeking. The names were diplomatic and practical, and they did not last. A German astronomer named Simon Marius had been making his own observations of the moons at roughly the same time, working independently and publishing his results several years later, in 1614, in a work he called Mundus Iovialis, the Jovian World. Marius had consulted the German mathematician Johannes Kepler when searching for names, and from that consultation came a different set, 4 names drawn from the ancient mythologies surrounding Jupiter himself. Io Europa, Ganymede, Callisto, figures from the old stories, companions and attendants of the god the planet was named for. The International Astronomical Union in the 20th century made those names official, and the 4 Galilean moons have carried them ever since. But the names came later, and in January of 1610, what existed was a set of ink marks on paper, and a man standing in the cold, learning something new every time the sky cleared. What he was learning, though he was careful about how he said it, was that the earth was not alone at the center of all things. This required care. In 1610, because the official picture of the cosmos, the one sanctioned by the Church, inherited from Ptolemy and Aristotle, refined and embedded over more than 1,000 years, placed the earth at the center of everything, motionless at the hub of concentric crystalline spheres that carried the moon and the sun and the planets and the fixed stars in their orbits around it. The Earth did not move. Everything moved around the Earth. This was not merely religious doctrine. It was also, in its way, the best available synthesis of ancient astronomical observation and philosophical reasoning. The alternative, the idea that the Earth moved, that the planets and the Earth all orbited the Sun, that the whole visible cosmos was arranged heliocentrically rather than geocentrically, had been proposed by Nicolaus Copernicus and published in 1543, but it remained a minority view, a mathematical convenience that some astronomers used to simplify their calculations without necessarily asserting it was a physical description of the actual world. What Galileo now had in his notebook was not a theoretical argument. It was an observed fact. 4 bodies were orbiting Jupiter, not the Earth. Jupiter, which meant that the Earth was not the sole center of all orbital motion in the cosmos. There was at least one other center, perhaps the Copernican argument that the Earth and all the planets orbited the Sun was not merely a useful fiction. Perhaps it was the shape of a real sky. Galileo was cautious in print, but the observation was there, and its implication was there, and anyone who understood orbital motion would understand what it meant to find 4 bodies circling a planet that was not the Earth. The pamphlet appeared in March of 1610. It was printed in Venice, which was at that time one of the great printing centers of Europe, a city whose press culture was vigorous and international and well connected to the networks of learned men across the continent. The title was Sidereus Nuncius, the Starry Messenger, or the Message from the Stars, depending on how the Latin was rendered. It was not a long document. It ran to a few dozen pages. It described 3 separate discoveries: the mountainous, cratered surface of the moon, which demonstrated that the moon was a solid, irregular, Earth-like body, rather than a perfect, smooth sphere; the existence of far more stars than the naked eye could detect, revealed by sweeping the telescope across the Milky Way; and the 4 bodies orbiting Jupiter, observed night after night, from January through the middle of March, their positions recorded in a series of woodcut illustrations that showed the same patient rows of dots and small circles that the notebook had already held. Approximately 550 copies were printed. This was a modest run, smaller than many popular books of the era, but the people who received copies were not ordinary readers. They were astronomers, natural philosophers, mathematicians, members of the courts of European princes, the secretaries, and scholars and curious noblemen who formed the network of learned exchange that crisscrossed the continent in letters and pamphlets and careful conversations. The pamphlet moved quickly. Within weeks of its publication, it was being discussed in letters sent from Venice to Prague, from Florence to London, from Rome to Paris. Some who received it were skeptical. The telescope itself was contested. If glass lenses bent and distorted the appearance of earthly objects, as critics pointed out, why should they be trusted to give a true image of celestial ones? Perhaps the points of light near Jupiter were artifacts of the instrument, optical illusions produced by the glass itself. This was not an unreasonable thing to wonder. The instruments were new, the optics imperfectly understood, the tradition of careful celestial observation suddenly interrupted by a device that no one had used for this purpose before. Skepticism was, in many cases, simply careful thought, but the observations were repeatable. The moons of Jupiter were not going to stop moving because someone doubted them. Other observers who obtained telescopes of sufficient quality could see the same points in the same positions on the same nights. Galileo had provided enough dated positions that another observer with a good telescope could check the predictions. The moons of Jupiter would be precisely where the record said they would be. They were. They were. They kept being exactly where the record said they would be, and the skepticism that was reasonable to hold in April of 1610 became harder to sustain in May, and harder still through the summer, as more observers pointed their own glass toward Jupiter and found the same 4 points arrayed in the same patient line. What the woodcuts in Sidereus Nuncius captured, pressed into paper by the force of a printing block, and dried in the March air of a Venetian print shop, was something that had never been captured before: the positions of 4 moons across 80 nights of observation, each position accurate, each one a small piece of an accumulated argument that nothing in the old sky could answer. The woodcuts were not art, exactly, they were records. But in being records so carefully and repeatedly made, they became something else, evidence of a method, a demonstration that the sky could be interrogated systematically, its behavior measured, predicted, and confirmed. The heavens were not a spectacle for the eye alone. They were a subject for instruments, and notebooks, and calculation, and return visits in the cold, night after night, until the pattern revealed itself completely. The moon in the sky does not change its relationship to Jupiter as the year turns. Jupiter remains. Jupiter, cream-colored and steady in whatever part of the sky it occupies in a given season. But everything about the meaning of that steady point of light changed in the winter of 1610 and the spring that followed, and the change was permanent. The ordinary winter sky, the sky that farmers had planted by, and sailors had steered by, and watchers had studied from rooftops and hillsides and open plains for thousands of years, was revealed to contain something it had always contained, but that no one had ever seen: 4 moons. Small and quiet and endlessly revolving, their paths as regular as breathing, their existence as certain as the planet they encircled. They had been there, moving in their careful orbits, for 4 billion years before a man in Padua steadied a brass tube and looked. They would have been there whether or not he looked. The discovery changed nothing about what they were doing. It changed only what was known, and it changed that completely, and the change did not stop at the edge of Galileo's courtyard. It moved, the way all real things move when the ground shifts, not explosively, but steadily, outward from the center, 1 letter at a time, 1 pamphlet at a time, 1 skeptical astronomer gradually convinced at a time, until the question was no longer whether the 4 points of light existed, but what it meant that they did. A scholar in Prague read the pamphlet in the spring of 1610 and set it down on his desk and looked out at the sky through a window. A natural philosopher in London received a copy in the summer and spent several nights trying to repeat the observation with a glass of his own. A mathematician in Florence, who had heard of the discoveries before the pamphlet arrived, wrote to Galileo asking for a copy before the ink was fully dry. The network of learned exchange that connected these men was slow by any later standard. Letters took weeks, pamphlets months, ideas the full span of seasons to propagate from one end of the continent to the other. But it was real, and it was working, and the argument was moving through it like light through a slow medium, bending and concentrating, and finally arriving, changed but still itself, at mind after mind after mind. The moons themselves were indifferent to all of this. Io moved in its orbit, close to the planet, swift. Europa followed, slightly farther out. Ganymede, the largest, turned in its own wide path. Callisto, outermost, completed its long circuit in 16.5 days, patient and steady, and unchanged by any of the interpretations being placed upon its existence. The 4 of them had been in those orbits since the solar system was young, since Jupiter itself had finished forming from the disk of gas and dust that surrounded the early sun, since the conditions that would eventually produce life on a small rocky planet in the inner system were still billions of years in the future. They were old in a way that is difficult to hold steadily in mind. The time between the formation of the Jovian moons and the night Galileo first saw 3 of them is longer than the distance between that night and the present day by a factor of roughly 400,000. They were ancient when the first fish crawled onto land. They were ancient when the first trees grew. They were ancient when the first human beings looked up at the sky and recognized Jupiter as a wandering light among the fixed ones. And they would continue their orbits, Io close and fast, Callisto wide and slow, long after the civilization that had finally looked at them carefully enough to see them has been replaced by whatever comes next. But in the winter of 1610, they were new to human knowledge, which is the only kind of newness that matters in this story. And the man who made them new to human knowledge stood in the cold with his instrument and wrote down what he saw, page after page, night after night, until the pattern was complete enough to put into print. Siderius Nuncius, The Starry Messenger. A short pamphlet, 550 copies, gone from the presses of Venice in March of 1610, and distributed slowly across a continent of scholars and curious readers and powerful men who liked to be seen reading the latest things. The woodcuts inside it, those small, patient rows of dots and circles, each dated, each positioned with care, were reproductions of the notebook drawings, translated into the medium of print so that many hands could hold them instead of only one. The man who made the observations and the man who read the pamphlet were not the same person looking at the same sky, but they were, in a sense, seeing the same thing. The woodcuts transferred the observation. They made the seeing portable. A reader in a candlelit room, somewhere in Germany or France or England, held the pamphlet and looked at the rows of illustrations and understood, if they were careful and patient enough, that 4 small bodies moved around Jupiter in the same way the moon moved around the Earth, and that this meant the Earth was not the only thing in the sky around which other things moved, and that this meant the old map of the cosmos, the one with the Earth at the center, motionless, everything else turning around it, had a problem in it that would not go away by being ignored. The problem was there, in the ink. It was there in the positions of 4 small moons on January 7th and January 8th and January 9th and all the other nights right through to March, each position a data point, and the whole sequence of positions an argument, not a philosophical argument, a factual one. The cosmos had been observed, and what was observed did not match the old map. The old map would need revising. This was not the end of the old map. Maps of the cosmos are not discarded in a single season. The revision took decades, and then generations, and the difficulties it created, the friction with established authority, the institutional resistance, the genuine philosophical complexity of reorienting an entire civilization's picture of its place in the universe. Those difficulties were real and serious and played out over the better part of a century. But the seed of the revision was in the pamphlet. The pamphlet was in 550 people's hands, and the hands spread across Europe slowly and inexorably and without any force other than curiosity and the ordinary human appetite for knowing what is true. One cold January night in Padua, 3 small points beside a planet, a man with a notebook and a steady hand and a brass tube and the patience to come back the next night and the night after. Whatever else happened afterward, The publications and the controversies and the long institutional argument and the vast restructuring of the human understanding of the sky, all of it grew from that ordinary cold night and those three ordinary small points of light. The points are still there. Jupiter is still there, cream-colored and steady, rising and setting with the patient regularity it has always had. On a clear winter night, from a dark field away from the lights of any city, it appears exactly as it appeared to every human being who ever looked at the winter sky before Galileo, a bright, unwavering point, slightly warmer in color than most of the stars around it. The largest planet in the solar system rendered into something a child could cover with a fingertip held at arm's length. But what the fingertip covers now is different from what it covered before. Not the planet. The planet is unchanged. Its four great moons moving in their orbits, just as they were moving in January of 1610, and just as they will be moving long after this particular winter has dissolved into the unrecorded past. What is different is the knowledge inside the mind of the person looking. The cream-colored point is not a wandering star in a sky built around the Earth. It is a planet, one of 8 in a solar system arranged around a single ordinary star, and it carries with it 4 worlds of its own, fire-surfaced and ice-covered, magnetic and ancient, each one a full and complex place, turning in their paths through space as they have always turned, as they were turning on the night they were first seen, as they will be turning long after the name Galileo has faded from every medium that holds it. The pamphlet moved across Europe in the spring and summer of 1610, carried by the ordinary mechanisms of an age that communicated in paper and ink and slow, careful letters. Scholars read it. Princes glanced at it. Skeptics put it down and then picked it up again. Astronomers trained their own imperfect instruments on the eastern sky and searched for the 4 points and found them and stayed up late writing down their positions. The starry messenger did what all genuine messages do. It arrived, and it changed the way the recipient understood where they were, and that change did not reverse when the pamphlet was set down, and the candle was blown out, and the night went quiet. The winter sky above Padua was the same sky that arched over all of Europe, the same sky that had been there for all of human history, and all the long history before that. It had not changed. But what could be read in it had changed. In the winter of 1610, because one man had the instrument, and the patience and the discipline to look carefully enough and write down what he saw. The message traveled outward from his notebook into print, and from print into the minds of the men and women of an entire civilization, and from their minds into the long accumulation of knowledge that would eventually become the picture of the solar system that anyone with a clear night and a pair of ordinary binoculars can now begin to see for themselves. The 4 points of light are still there, patient, still, turning, beneath the surface of Io, where no surface can be seen and no light has ever reached. The rock is moving, not in any way that would register as motion in a single lifetime, not in any way that produces sound or sign visible from outside. The rock moves the way a slow breath moves, drawn in, held, released over the long hours of each orbit, pulled and compressed and stretched by a force that never pauses and never relents. The moon circles Jupiter in 42 hours. In each of those hours, Jupiter's gravity reaches into Io's interior and bends it ever so slightly out of round. That bending generates heat. Not the heat of burning, not the heat of a chemical reaction finding its end point, but frictional heat, the kind that comes from 2 surfaces working against each other, from the sheer persistence of resistance over time. Io's interior is not burning. It is being kneaded the way a hand kneads clay, except the hand is gravitational and the clay is a world 400 million miles from Earth, and the kneading has been going on for billions of years without a single pause between pulls. This is the source of everything that happens on Io's surface, everything visible, everything volcanic, everything that makes this moon the most geologically active object in the solar system. All of it traces back through chains of heat and pressure and slow convection to the simple, persistent fact that Io's orbit is not quite circular. Because the orbit is slightly elliptical, Io's distance from Jupiter changes as it travels, and Jupiter's gravitational pull changes with it, and the moon flexes inward and outward, fractionally but continuously, in response to a force it can never escape. The reason the orbit stays elliptical, rather than gradually circularizing the way an orbit might if left alone, is that Io is not alone. Europa and Ganymede travel with it, each moon completing its own orbit in a precise relationship to the others. For every 4 times Io circles Jupiter, Europa circles twice, and Ganymede circles once. This is a resonance, a gravitational rhythm maintained by the repeated synchronized pulling of 3 worlds on each other. And that rhythm is what keeps Io's orbit from rounding out, what keeps the tidal flexing from easing, what keeps the interior warm. The heat in Io's mantle is in a sense the heat of a relationship, a 3-way gravitational conversation that has been running in the same meter for the age of the solar system. From outside, the moon is a small and vivid sphere. In images returned by spacecraft, Io's surface appears in yellows and oranges and blacks and occasional pale whites, like a sphere painted with cooling sulfur, like a world that has been heated from beneath so thoroughly and for so long that its entire outer skin has been rewritten in volcanic material. There are no impact craters visible on Io's surface, which is itself a kind of fact about time. Craters form when meteorites strike, and they accumulate on surfaces that are not being constantly renewed. Io's surface is constantly renewed. Lava flows cover older lava flows. Volcanic deposits bury everything. Whatever craters once existed are long gone beneath the steady accumulation of a world that cannot stop producing new material. The surface is also extremely cold. That is the other thing about Io that takes some settling into. The volcanic features are intensely hot, locally, but the moon sits more than 5 times farther from the sun than Earth does, and the space around it is very cold. And so Io's surface outside the active volcanic zones is a place of sulfur dioxide frost and temperatures far below what any thermometer on Earth would register as bearable. The moon is hot on the inside, cold on the outside, and what happens on the surface is the result of those 2 conditions meeting. On March 5th, 1979, a navigation engineer named Linda Morabito was examining images returned by the Voyager 1 spacecraft, which had passed through the Jovian system just days before. She was working with one of the images to locate a star field for navigational purposes, brightening the image to make the stars more visible. What she found in the brightened image was something that did not belong to any star field. Rising above the edge of Io's disk, curving upward in a broad, delicate arc, was a structure she had not expected. It was a plume, a volcanic plume, rising more than 300 kilometers above the surface, its shape preserved in the long exposure of the image, like a frozen fountain. Nothing like it had ever been observed on another world. Scientists had expected Io to be geologically quiet, a dead rock frozen in the cold distance from the sun. What Morabito saw was the opposite of quiet. The plume she observed rose from a volcano called Pele, one of Io's largest and most persistent volcanic features. Pele's plume is not a small thing. It reaches upward more than 300 kilometers, an umbrella-shaped arc of ejected material, moving against the black of space in absolute silence, since sound requires a medium and space provides none. The material that rises through the plume is sulfurous, sulfur dioxide, sulfur monoxide, various sulfur compounds that turn from gas to solid as they rise into the cold and that fall back slowly under Io's gravity in a great slow-spreading curtain. The deposits left by Pele form a dark red ring on the surface more than 1,000 kilometers across. That ring is the shadow of a plume that has been operating on and off for a very long time. Io's gravity is weaker than Earth's, less than 1/5 as strong, and that low gravity is part of what allows the plumes to rise as high as they do. On Earth, an explosion of comparable force would push material far less high against the stronger pull of the planet. On Io, material ejected at volcanic speeds can travel hundreds of kilometers upward before gravity bends its arc and pulls it back. The plume hangs for a long time before the material begins to fall, and when it falls, it does so slowly enough that the spreading pattern creates those distinctive rings, annular deposits of colored sulfur compounds on the surface, marking the reach of each plume like a painter's brushstroke applied in slow motion from 300 kilometers above. The largest volcanic feature on Io is not a mountain and not a plume. It is a lava lake. Loki Patera covers an area more than 200 kilometers across, a sheet of liquid and semi-liquid rock held within a roughly horseshoe-shaped depression in the surface, so large that it would stretch across the state of Kansas with room to spare on either side. Loki Patera is not static. It undergoes a cycle in which the cooled solidified crust that forms on the lake's surface gradually sinks as the denser cooling rock becomes heavier than the liquid beneath it. When the crust sinks, fresh, hotter material is exposed, and the cycle begins again, a slow, regular overturning of the surface that has been tracked by telescopes on Earth, watching the brightening and dimming of Io's thermal signature as each new section of hot material is exposed. The cycle repeats roughly every year and a half. One side of the lake seems to overturn first, the wave of fresh material moving around the lake in a slow, regular progression, the hot glow traveling like a clock hand before fading again as the surface cools. From far away, through a telescope measuring only the heat, this overturn appears as a predictable rhythm, a thermal pulse from a world 2.5 billion miles distant. The pulse tells the observer that the lake is still active, that the heat source driving it is still running, that Jupiter's gravitational pull has not relented. Alongside the lava lakes and plumes, Io has volcanic features called paterae, broad, shallow, flat-floored depressions where lava has pooled and cooled in place. And it has mountains, actual mountains, enormous folded ridges of compressed silicate rock pushed up not by volcanic construction, but by horizontal compression in the crust. Some of Io's mountains are tall enough to rival the highest peaks on Earth, reaching upward in sharp, heavily eroded ridges above a surface otherwise dominated by volcanic plains. The combination of compressed mountains and spreading volcanic deposits produces a landscape unlike anything in the inner solar system. Ridges of deep rock rising through sulfur-stained plains, their flanks yellow and orange with volcanic fallout, their peaks too high for the low gravity to smooth away quickly. One particularly well-studied volcanic region is called Tvashtar Paterae, a chain of volcanic features in Io's northern polar region. When the New Horizons spacecraft passed through the Jovian system in 2007, On its way to the outer solar system, its cameras caught Tvashtar producing a curtain of lava several hundred kilometers long. The image shows the lava curtain as a bright, deep orange line against the dark surface of Io, steady and continuous, a wall of liquid rock burning against the cold black of space, with no atmosphere to diffuse the light, no haze to soften the edge. The curtain hangs there in the image, patient and enormous, more like a geological feature than an event, not an explosion, but a sustained outpouring, the interior of a moon pressing steadily outward through a crack in its own surface. The interior of Io has never been directly measured, but from the way the moon responds to the tidal forces and from the heat it emits, the best current picture is of a deep, partially molten mantle underlying a thin crust. The mantle is not fully liquid. It is more like a material that is partly solid and partly molten, a mixture that can flow under sustained force, but that behaves like a solid under rapid impact. Jupiter's gravitational pull works on this material the way a steady hand works on very thick clay, slowly, persistently, deforming it slightly with each pass before the material's own resistance partially restores its shape. The heat generated by this process is conducted upward through the crust and released at the surface, appearing as volcanic activity wherever the crust is thin enough or fractured enough to allow the heat through. The amount of heat Io releases is much larger than what the sun contributes to the moon's surface. Io produces more heat from its interior per unit of surface area than Earth does from its own interior. Earth's interior heat is the residual warmth of its formation and the decay of radioactive elements in its interior, and it is enough to drive Earth's plate tectonics and volcanism. But Io's tidal heating produces a flow of heat through the moon's surface that is in some regions more than 10 times greater than Earth's average geothermal output. This is not a world that has been cooling since its formation. In some respects, and by some measures, Io may be hotter now in its interior than it was when it formed, because the tidal resonance has been building heat in the interior since the orbital resonance stabilized billions of years ago. Beyond the heat and the lava and the plumes, Io does something that no other moon in the solar system is known to do in quite the same way. As it moves through Jupiter's magnetic field at roughly 57,000 kilometers per hour along its orbital path, the moon acts as a conductor moving through a magnetic environment. The interaction generates an electrical current, not a metaphorical current, not a gentle drift of charged particles, but a genuine flow of electricity, approximately 5 million amperes moving along magnetic field lines, connecting Io to Jupiter's polar regions. The cable is not a wire. It is a channel of plasma, of ionized gas, threaded along the magnetic geometry of the Jovian system. 5 million amperes is a figure without a good human comparison, but to approach it from a different angle, the entire electrical generating capacity of the United States, all of it running simultaneously, falls well short of what flows continuously along the Io flux tube. It flows not because anyone is running it, not because any switch was thrown, but because an electrically conducting body is moving through a magnetic field, and that is what electrically conducting bodies do in magnetic fields. The current does not disappear into space. It arrives at Jupiter. Along the magnetic field lines connecting Io's orbit to Jupiter's polar regions, the charged particles accelerate downward into Jupiter's upper atmosphere and produce aurora, a shimmer of ultraviolet and infrared light at the planet's poles that traces the exact position of Io's magnetic footprint on Jupiter's cloud tops. Jupiter's poles glow, faintly, because Io is there. The aurora shifts as Io moves, tracking the moon's position in its orbit like a shadow thrown by an invisible lamp. When Io passes into Jupiter's shadow and is eclipsed, the flux tube dims. When Io emerges, it brightens again. The aurora is a readout, a slow, soft display on the face of a giant planet, reporting in light the continuous motion of a volcanic moon hundreds of thousands of kilometers away. The volcanic gases that escape from Io's surface do not all fall back to the moon. Some of them are ionized by solar radiation and by the intense radiation environment of Jupiter's magnetosphere, stripped of electrons, transformed from neutral gas into charged particles, and once ionized, they cannot simply fall back under gravity the way neutral gas might. They are captured by Jupiter's magnetic field. They are swept along Io's orbital path. Slowly, over time, they spread into a broad donut-shaped ring of plasma surrounding Jupiter at approximately the distance of Io's orbit. This structure is called a plasma torus. It is invisible to the naked eye, and it is invisible even to most cameras, unless those cameras are looking in the right wavelengths. But it is there, enormous, surrounding Jupiter in a pale ring of glowing ionized material, its composition reflecting the composition of Io's volcanic output: sulfur, oxygen, sodium, potassium, a signature of the moon's interior chemistry written large in the space around the planet. The plasma torus is not static. It rotates with Jupiter's magnetic field, which rotates faster than Io orbits, and so the interaction between the torus and the moon is continuous, Io moving through a field of its own effluent, the plasma it shed earlier, now sweeping past it again, and the interaction between the moon and the torus, contributing to the currents and the aurora. The system is interconnected in ways that took decades of spacecraft observations to begin to untangle. What began as a simple question, why is Jupiter's magnetosphere so much more energetic than would be expected, resolved over years of measurement into the answer that Io is continuously supplying it with material and energy, several hundred kilograms of new plasma per second flowing from the moon's volcanic output into the broader magnetic environment. Io does not simply exist within Jupiter's magnetic system, it actively shapes it. The first spacecraft to study Io closely was Voyager 1 in 1979, and the findings from that single flyby overturned the expectation that the outer solar system's moons would be cold, geologically dead worlds. In the years since, the Galileo spacecraft studied Io in many orbits through the 1990s and into the early 2000s, measuring the heat flow, the magnetic environment, and the composition of the volcanic material. Later, the New Horizons spacecraft captured images of the Tabsatar lava curtain during its brief passage through the system, and Earth-based telescopes, growing steadily more capable over the decades, have continued to track the thermal rhythms of Loki Patera, watching the lake's overturn cycle from a distance of hundreds of millions of miles, reading the heat signature of an active world from across the solar system. The Juno spacecraft, which entered Jupiter orbit in 2016 and has been extended through the 2020s, has made close flybys of Io, returning images and measurements of the volcanic surface at a resolution that earlier spacecraft could not achieve. Among the features visible in Juno's images are active lava flows, newly formed deposits from recent eruptions, and thermal hotspots, places where the surface is noticeably warmer than its surroundings, where fresh volcanic material has reached the surface recently and has not yet cooled. The surface of Io that appears in Juno's images is not the same surface that Voyager saw in 1979. It has been resurfaced, in part. New material has covered old features. Eruptions that did not exist in 1979 have come and gone. Io is not the same moon it was when humans first photographed it. There is something settling about the process, considered at the right scale. Io is doing what it has been doing for billions of years. Jupiter's gravity is pulling at it. The resonance with Europa and Ganymede is maintaining the elliptical orbit. The interior is warm. The surface is erupting. The plumes are rising and falling. The plasma is flowing outward into the torus. The current is threading down the flux tube to Jupiter's poles. None of this is new. None of this is urgent. It is a system in a kind of steady state, not unchanging, but continuously renewing itself through the same processes, driven by the same forces, at roughly the same pace, for a time so long that the specific eruptions and flows and deposits within it are entirely temporary against the backdrop of the system's continuity. Each of Io's volcanic eruptions is, from one perspective, a dramatic event: lava fountains and plumes and ash deposits, and flows covering hundreds of square kilometers. From another perspective, each eruption is just one more moment in a process that has been running without essential interruption since before the Earth had any complex life on its surface. The scale at which Io's volcanic activity is dramatic is the scale of a single eruption, a single year. The scale at which it is calm and rhythmic and self-sustaining is the scale of a solar system, a geological epoch. At that larger scale, the lava curtain at Tvashtar is not a crisis, but a feature. The overturn of Loki Patera is not a disturbance, but a pulse. In the darkness between Io and Jupiter, where the plasma torus spreads its invisible ring of ionized sulfur and oxygen, the material that came from the moon's interior sits suspended in magnetic space, slowly drifting, gradually mixing into the larger magnetosphere, eventually lost into the broader Jovian environment. The sodium and sulfur that erupted from beneath Io's surface, that rose in a plume above the surface and was ionized by radiation and swept into orbit, is now part of something much larger than the volcano that produced it. It is part of Jupiter's magnetic system. It influences the radiation environment around the giant planet. It shapes in small ways the conditions experienced by the other moons. With the heat that began as tidal friction in Io's mantle has traveled through many transformations into the space around Jupiter, carrying the signature of the moon's interior chemistry far from its source. The 5 million amperes flowing along the flux tube arrive at Jupiter's atmosphere as aurora. That aurora is one of the brightest ultraviolet features in the solar system. It glows at the poles of a planet larger than 1,000 Earths, driven by the volcanic exhaust and the electrical conductivity of a moon smaller than the Earth's own satellite. The scale relationship is extraordinary in one direction and then entirely ordinary in another, a small moon shaping a large planet's atmosphere because the physics of moving conductors in magnetic fields does not know or care about the difference in size between the generator and the load. Io carries its heat with it always. The core of the moon, wherever heat concentrates, wherever the tidal flexing squeezes hardest, is warmer than the surrounding rock, and that warmth conducts outward and upward through the mantle, reaching the base of the crust, finding the weaknesses and the fractures and the thin places in the rock above, pressing through them in slow convective columns toward the surface. The heat that left the interior last week might not reach the surface for some time still. The heat that is reaching the surface now has been traveling upward for longer than recorded human history. It is patient heat, moving through solid rock at the pace rock allows, arriving eventually at the surface as a volcanic eruption, a thermal hotspot, a sulfurous plain still warm to whatever instrument might be placed upon it. On the surface of Io, in the broad yellow plains between the volcanic centers, sulfur dioxide frost settles from the thin atmosphere, an atmosphere so thin it barely deserves the name, a few molecules thick in most places, slightly denser above the volcanic regions where outgassing continually replenishes it. The frost is brilliant white where it is accumulated undisturbed, and it is fragile in the radiation environment around Jupiter, darkening and changing color under bombardment by high-energy particles. In some places the surface is layered, old frost beneath new deposits. The geology of the surface, readable in layers, the way geological strata are readable on Earth, each layer recording a period of activity and deposition. The whole surface is a record, but a short one by geological standards. Because Io is so volcanically active, the surface is young. The oldest visible surface features date back perhaps 1 million years, a small number in the context of the solar system's 4.5 billion year history. What happened to Io's surface before that is buried. The craters from the early bombardment that scarred every other moon in the solar system buried. The early volcanic structures that formed when Io was first captured into the resonance buried. The record is continuously overridden, continuously renewed, each new layer of volcanic material covering what came before and starting the count again. This is part of what makes Io unusual among the moons. Most moons in the solar system are archives. Their surfaces preserve very old records. Their geology speaks in the language of ancient impacts and ancient tectonics long since frozen. Io's surface refuses to preserve anything for long. It is not an archive. It is more like a working place, continuously in use, never allowed to settle long enough to become a relic of something past. The past is there, beneath the surface, but invisible, buried under the output of a process that has been running since before the Earth's continents had their present shapes. And so the moon continues in its orbit. Every 42 hours, it completes another circuit of Jupiter. With each circuit, the gravitational interaction with the planet squeezes and releases the interior one more time. The heat produced in the mantle by that one circuit is small in isolation. Over a year, it becomes significant. Over 1 million years, it has melted and resurfaced an entire world. Over the age of the solar system, it has made Io what it is, the fire that does not rest, the surface that cannot keep a single scar, the moon that charges Jupiter's poles with aurora and fills the space between them with a slow, invisible river of volcanic gas transformed into light. Deep in the magnetic field lines connecting Io to Jupiter, where the electrical current of 5 million amperes threads its silent path from the moon to the planet's polar atmosphere, the charged particles move without friction and without sound through the cold of space. At the far end of that current, at Jupiter's poles, the aurora shifts and pulses in response to Io's motion, a faint shimmer in the ultraviolet, not visible to the eye but present, steady, reliable, a light that will still be burning in the same way long after anything human has had a chance to observe it. That light comes from Io's heat. That heat comes from Io's motion. That motion comes from Jupiter's gravity, and from the gravitational conversation among 3 moons in resonance. The plasma torus glows around it all, invisible and patient, a donut of volcanic exhaust suspended in magnetic space, neither fully attached to the moon that made it, nor fully part of the larger system that holds it. It is in between, part of Io and part of Jupiter and part of the space between them, a reminder that a moon's interior life does not stay interior for long. What begins deep in the rock, as heat generated by nothing more than the persistence of gravity, finds its way outward through every boundary available to it until it has become part of something larger and older and stranger than any single volcanic vent or lava lake or sulfur plain could contain. From a great distance, Europa appears almost featureless. It is a pale sphere, close to white, smooth enough at first glance that the eye slides off it without finding purchase. Against the dark of space, and against the vast orange and cream of Jupiter turning slowly beside it, Europa looks quiet. It looks cold. It looks like a world that has been still for a very long time. But the closer the eye moves toward that surface, the more the whiteness begins to resolve. Lines appear, thin at first, faint reddish-brown marks curving across the ice like the grain of old wood, and then thicker ones and darker ones, crossing and branching and running for hundreds and hundreds of kilometers without stopping until the entire surface of the moon is revealed as a pale field covered in a dense, irregular cross-hatching of color. The lines are everywhere. They intersect without order. They curve around the curvature of the moon and disappear over the horizon and continue on the far side. There is no part of Europa's surface that is not marked by them, no region of clean, unbroken ice that has not been cracked and refrozen and cracked again in a slightly different place. That surface is water ice. The entire outer shell of this moon is frozen water, compressed by the cold of deep space into a crust that holds its shape under pressure and floats on something below. The lines crossing it are the record of movement, of the slow and continuous bending of that crust under forces that have not stopped acting on it since the moon first formed. They are called linea, from the Latin word for lines. A better description might be scars, though the word carries more weight than the process requires. Each one marks a place where the ice cracked under stress, where the gap opened and something welled up from below and then froze again before the gap could widen further. Then the stress returned, and the cycle began in a slightly altered place. The forces doing this are gravitational. Jupiter, enormous and close, pulls on Europa with a grip that changes fractionally as Europa moves through its slightly elliptical orbit, coming a little closer to the giant planet and then drawing a little further away in a rhythm that repeats once every 3.5 days. That small change in distance means a small change in gravitational force, and that small change in force, acting on an object as large as a moon, produces a small but measurable deformation of the entire body. Europa stretches and relaxes. It flexes. The ice on its surface bends with it, and where the bending exceeds what the ice can absorb without breaking, it cracks. The crack fills. The moon continues in its orbit. This process is called tidal flexing, named for the same family of forces that raise the ocean tides on Earth each day. On Earth, the tidal force acts on liquid water and produces a rise and fall of a few feet along the coast. On Europa, the tidal force acts on an entire moon, and what it produces is the wholesale cracking and reshaping of a world's outer shell, over and over, in a process that has continued without interruption for billions of years. Europa does not travel this orbit alone. It is locked into a precise gravitational relationship with two other moons of Jupiter, each one's orbital period standing in an exact numerical ratio to the others. For every one time Europa circles Jupiter, the moon just inward completes almost exactly 2 orbits. For every 2 times Europa circles Jupiter, the moon just outward completes almost exactly 1. These relationships are not coincidental. Gravity enforced them over long time, drawing the 3 moons into a configuration that reinforces itself, that resists disruption, that persists. The name for this configuration is orbital resonance, and the specific arrangement of these three moons is called the Laplace resonance, after the mathematician who first described its properties. What the resonance does, beyond maintaining those precise orbital ratios, is keep Europa's orbit slightly elliptical rather than perfectly circular. A perfectly circular orbit would produce a constant gravitational pull from Jupiter, and without variation, there would be no flexing. The elliptical orbit produces the variation, and the variation produces the flexing, and the flexing produces heat. That heat is the key. In the cold of the outer solar system, far from the warmth of the sun, a small moon made of rock and ice should be frozen through. The sun at Jupiter's distance delivers only about 4% of the energy it delivers to Earth. There is no way for sunlight alone to keep water liquid inside a moon at this distance, but tidal flexing generates heat directly within the interior of the moon, not by warming the surface from outside, but by the continuous mechanical working of rock and ice against itself, friction on a planetary scale, slow and deep and steady, and that heat is enough. It is enough to maintain, somewhere beneath Europa's frozen surface, a layer of liquid water. The evidence for that ocean did not come from direct observation. No instrument has yet penetrated Europa's ice. The evidence came instead from something subtle and indirect, from the behavior of the moon's magnetic environment. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, carried a magnetometer designed to measure the magnetic field in the space around each of Jupiter's large moons. When the spacecraft flew past Europa, the magnetometer detected something that had not been expected. Europa's magnetic environment was changing in a specific way, oscillating in response to changes in Jupiter's own powerful magnetic field, and the character of that oscillation matched almost exactly what would be produced by a layer of electrically conductive material somewhere beneath the surface. Salt water conducts electricity. A global layer of liquid, salty water beneath Europa's ice, exposed to Jupiter's changing magnetic field, would generate exactly this kind of oscillating magnetic response. The detection was not a measurement of the ocean itself. It was a measurement of the ocean's magnetic shadow, the faint imprint it left on the space around the moon. From that shadow, the scientists working with the Galileo data concluded that the ocean was real, that it was global, that it extended around the entire moon beneath the ice, and that it was conductive, which meant it was not pure water, but water with dissolved salts, the chemistry of an ocean rather than a lake. The volume of that ocean, estimated from what is known about the thickness of the ice above it and the radius of the rocky body below, is very large. The total amount of liquid water beneath Europa's ice is believed to be roughly twice the combined volume of all the oceans on Earth. Every sea and bay and river and lake on this planet gathered together and doubled, and yet this ocean is invisible from the outside, sealed beneath kilometers of ice, in a darkness that no light of any kind has ever entered. The ice above it is the shell that does the bending and cracking. How thick that shell is remains a question the data can answer only approximately. Estimates from different lines of evidence suggest a minimum of a few kilometers and possibly as much as 30. At the thinner end, the ice would be flexible enough that the ocean below might interact more directly with the surface, cycling material upward through the shell over time. At the thicker end, the ice would be more rigid, the ocean more thoroughly sealed from the surface. The truth is somewhere in that range, and determining it more precisely is one of the central goals of future investigation. What can be observed directly from orbital imagery is that Europa's surface is not static. It shows evidence of deformation, of regions where the surface has been pulled and twisted and partially renewed. The most striking of these regions are called chaos terrain, places where the ice looks as though it has been broken into large irregular pieces that have been shuffled out of their original positions and then frozen in place. One of the best studied examples of this is in a region called Connemara Chaos. There, large plates of older, more heavily patterned ice appear to have drifted apart from each other, rotated slightly, and come to rest in new positions, with the gaps between them filled by younger, smoother ice that welled up to fill the space before freezing. What Connemara Chaos looks like, in orbital images taken from several hundred kilometers above, is a field of ice blocks the size of small cities, each one tilted slightly at an angle to its neighbors, each one's surface still carrying the pattern of linea from before whatever disruption moved it. Those patterns now misaligned with the plates on either side, like the pieces of a puzzle pressed back together incorrectly. The younger ice between them is smoother, less marked, almost featureless compared to the ancient fractured surfaces of the plates themselves. It is, in the most literal sense, a record of disruption frozen in place. The disruption probably involved the partial melting or softening of the ice from below, perhaps during a period of elevated tidal heating, when more heat came up through the shell than usual. The glice above the warm region became soft enough to move, the plates drifted, the heat decreased or redistributed, the ice refroze. Whatever had been briefly fluid became solid again, locking the plates in their new positions. The whole event left a record on the surface that can still be read billions of years after it ended. The surface of Europa is young by geological standards. Impact craters, which accumulate on planetary surfaces at a rate that depends on how much debris is present in the vicinity, are rare on Europa. In the inner solar system, a surface that old would show thousands of craters. Europa shows far fewer, which means that whatever craters were made on its surface have been erased by the continuous geological activity of tidal flexing and ice recycling. The surface is being remade. Old ice is removed, and new ice takes its place. The geological clock is continuously being reset. The floor of the ocean, on the other hand, has not been reset. It is silicate rock, the substrate beneath the water, and it has been in contact with that ocean for as long as the ocean has existed. On Earth, the interface between ocean water and rocky seafloor is one of the most chemically productive environments in the world. Water percolates through fractured rock, reacts with minerals, exchanges heat, and emerges carrying dissolved material into the water column. Hydrothermal vents, where particularly warm and chemically enriched water rises through cracks in the seafloor, support dense communities of life in environments where sunlight never arrives, sustained entirely by the chemical energy of the water itself. The idea that something analogous might exist on Europa's seafloor is not a leap of imagination. It follows from what is already established. There is a rocky floor. There is liquid water in contact with it. There is a persistent heat source, tidal flexing, that has been operating for billions of years. Whether the heat is sufficient to drive hydrothermal circulation at the sea floor is not yet known. The chemistry of the ocean, whether it carries the right dissolved materials in the right concentrations, is also not yet known. The questions are real, and the answers are not yet in hand. What is in hand is the understanding that the physical conditions present on Europa are conditions under which, on this planet, liquid water in contact with rock and heat has consistently produced environments where the chemistry of life is possible. That is not a statement about life on Europa. It is a statement about what the physical setting provides and about why that setting is taken seriously by scientists who study the boundaries of habitability. The concept of a habitable zone traditionally referred to the band of distances from a star at which water could exist as a liquid on a planetary surface. Europa extends that concept. It shows that liquid water can persist in the outer solar system, far beyond what had been considered the outer edge of any plausible habitable zone, sustained not by sunlight, but by the tidal forces of a nearby giant planet. The habitable zone, as understood before Europa, was a ring around a star. Europa suggests it may be a different and more complex thing. The ice shell itself contributes to this picture in another way. The linea running across its surface are not only records of cracking, they also carry material. When the ice opens and closes, it can transport chemical compounds from the surface down into the ice, and over long cycles, possibly deeper. Europa's surface is bathed in radiation from Jupiter's magnetic environment, intense enough to drive chemical reactions in the ice at the surface level, producing oxidizing compounds that would not otherwise form in such abundance. If those surface-produced compounds can be cycled downward through the ice shell into the ocean over geological time, they would change the ocean's chemistry in ways potentially significant for the kinds of reactions that sustain biology on Earth. Whether that cycling occurs efficiently is again not yet established. It is one of the questions that current investigation is designed to begin answering. In October of 2024, a spacecraft named Europa Clipper left Earth and began a trajectory toward the Jovian system. It will not arrive quickly. The journey is measured in years, the path designed to carry the spacecraft through a series of gravitational assists from other planets before it reaches Jupiter. When it does arrive, it will not attempt to orbit Europa directly because the radiation environment close to Jupiter is severe, and a spacecraft in continuous close orbit of Europa would accumulate damage faster than its systems could sustain. Instead, Europa Clipper will orbit Jupiter itself, executing a series of close flybys of Europa, each one passing low over a different region of the surface, each one collecting measurements with the instruments arranged in its body. Those instruments include a magnetometer, which will make much more precise measurements of Europa's induced magnetic field than the Galileo spacecraft was able to achieve, measurements that should allow a more exact determination of the ocean's depth, salinity, and extent. A mass spectrometer will analyze the thin material that escapes from Europa's surface and immediate environment, sampling its chemical composition in a way that can begin to characterize what the surface and ice are made of. A radar designed to penetrate ice will send pulses downward through the shell and listen for the echoes returning from different depths, looking for the signature of liquid water beneath solid ice, measuring the thickness of the shell from above. The spacecraft also carries cameras, a thermal imaging system, a magnetic sounder that can map the electrical conductivity of the ice, and instruments designed to measure charged particles and the ultraviolet emission of the surface. 9 scientific instruments in total, each contributing a different layer of information about a world that for all of human history, until the late 20th century, was nothing more than a faint point of light visible to the right kind of telescope circling a bright planet in the eastern sky. Europa Clipper will conduct dozens of flybys over the course of its mission. Each one will last only a matter of hours, the spacecraft sweeping in close at high speed, gathering data as it passes, then receding as its orbit carries it away again. Across all those flybys, the instruments will build up a comprehensive picture, one overpass at a time, of the ice, the ocean, the chemistry of the surface, and the magnetic environment. The picture will not be complete when the mission ends. It will be far more complete than anything that exists now, and it will shape what comes after. The spacecraft moves through the cold and the dark of the outer solar system at speeds that are difficult to anchor in familiar terms. It crosses distances that take light itself many minutes to travel, and yet it moves slowly enough that the journey takes years, that each flyby must be planned in great detail long before the spacecraft arrives, that the measurements taken during a few hours of close approach will be analyzed for decades afterward. The pace of the mission is not the pace of urgency, it is the pace of careful, deliberate inquiry, carried out over timescales that dwarf those of ordinary human attention. There is something fitting in that pace. Europa has been waiting, if the word can be allowed without implying intention, for 4 billion years. Its ocean formed long before life on Earth grew complex enough to look outward and wonder about other worlds. The ice sealed over the water during an era when the most sophisticated life on this planet was still single-celled. Whatever has or has not happened in that ocean since then has been happening in total darkness, under kilometers of ice, in a silence that has never been interrupted from outside. Against that timescale, the years it takes a spacecraft to cross the solar system are a brief moment, a swift thing. The ice at Europa's surface is kept near the temperature of deep space, more than 100 degrees below the freezing point of water. At that temperature, the ice is hard in a way that feels different from the ice of a mountain glacier, which is pliable and flows over centuries. Europa's surface ice is rigid and brittle, cracking cleanly under stress rather than flowing. Below it, with increasing depth, the temperature rises. The tidal heat coming up from within the moon warms the deepest ice until at some depth that may range from a few kilometers to tens of kilometers below the surface, the ice reaches its melting point and becomes water. The transition is not an abrupt wall, and it is a gradient, the ice becoming softer and more pliable as the temperature rises, until the transition to liquid is complete and the ocean begins. Below the ocean, the floor of rock is held at a pressure created by the weight of the water above. The pressure at the deepest points of Europa's ocean, if those depths are comparable to the deepest ocean trenches on Earth, would be enormous. On Earth, life exists in comparable pressures. The organisms living at the bottom of the Mariana Trench, nearly 7 miles below the surface of the Pacific, have been under crushing pressure for as long as their lineages have inhabited that environment. Pressure, like darkness and cold, is a constraint that life on Earth has proven repeatedly capable of working within, though the methods differ from one organism to the next, and the solutions found in one extreme environment are not always the same as those found in another. Europa Clipper does not carry instruments designed to detect life directly. That is a deliberate choice, not a limitation of interest, but a matter of scientific sequencing. Before asking whether life is present, the mission is designed to determine whether the conditions for life are present, to characterize the ocean's chemistry and energy sources, and the stability of its environment, to build the foundation of knowledge on which a more targeted future investigation could stand. The scientific reasoning is that a positive detection of life, if made by instruments not specifically designed for that purpose, would be very difficult to verify and very difficult to interpret. The better path is to first understand the environment thoroughly, and then, in a subsequent mission, approach the question of biology with instruments designed for exactly that purpose, on a target that has been characterized well enough to know where and how to look. That subsequent mission does not yet exist beyond the planning stages. It is a thing that belongs to the future, to a generation of scientists and engineers who are at various points in their careers, or still in school, or not yet born. By the time instruments are sent to directly sample Europa's ocean, if that ever comes to pass, the work being done now by Europa Clipper will form the essential background against which those results are interpreted. What Europa Clipper will find is not yet known. The scientific community has a range of predictions and expectations informed by existing data and theoretical models, but the moon has been characterized precisely enough to expect surprises. Every previous close investigation of a solar system body has returned unexpected findings alongside the expected ones. The surface of Europa has already shown features that were not clearly predicted before they were seen, regions where the ice has behaved in ways that are still being debated and explained. The reddish-brown color of the linea is itself a subject of active investigation. The ice of Europa's surface is not uniformly white. The coloring agent in the disrupted regions appears to be a complex mixture of salts and organic compounds, possibly cycled up from the ocean below, or produced by the interaction of Jupiter's radiation with material in the ice. Sulfur compounds, chlorides, magnesium salts, various candidates have been proposed. The mass spectrometer on Europa Clipper is designed to help resolve this question by directly sampling the material escaping from the surface into the thin envelope of gas and particles surrounding the moon. There is evidence, still being carefully assessed, that Europa occasionally releases plumes of material from beneath its ice, as the Hubble Space Telescope detected possible water vapor outgassing from the moon on at least 2 occasions. If such plumes exist and are active during the Europa Clipper flybys, the spacecraft's instruments will be positioned to sample them directly, passing through the ejected material and analyzing its composition at close range. The plumes, if real, would offer an extraordinary window into the ocean below, carrying material from within the moon out into space, where it could be measured without the need to penetrate kilometers of ice. Their existence is not yet confirmed with certainty. The measurements that would confirm or rule them out are among those Europa Clipper is designed to make. The ocean beneath Europa's ice exists in a darkness so complete that no analogy involving ordinary dark quite captures it. The darkest night on Earth admits some fraction of starlight, and the atmosphere scatters that light faintly in every direction. The deepest cave on Earth connects, ultimately, to the outside world through fissures and passages. The inside of Europa's ocean is sealed by kilometers of ice from every photon that has ever been generated in the history of the sun. The water there has never been warm in the way surface water anywhere in the solar system is warm. Whatever chemistry occurs in that ocean occurs without light, driven by heat and dissolved minerals, and the slow exchange of material between water and rock. On Earth, the chemical energy available in hydrothermal environments, the oxidized compounds produced at the surface and mixed downward, the dissolved gases from volcanic activity, these are enough to sustain complex metabolisms without sunlight. The organisms that live in those environments do not experience them as inhospitable. They are precisely adapted to the chemistry and the pressure and the temperature, and they thrive in conditions that would kill any organism adapted to the surface world within seconds. Life on Earth has found ways to exist in circumstances defined by constraint and defined by the chemistry available in that particular place, and the definition of what constitutes a viable environment has expanded with each new extreme ecosystem that has been explored. None of this establishes that life exists in Europa's ocean. That question remains fully open, with no evidence pointing definitively in either direction. What it establishes is that the question is not answerable by inspection from a distance. It requires the kind of careful, incremental investigation that the current mission represents, and the kind of more direct investigation that would follow from it if the results warrant. The open question is not a source of anxiety or urgency. It sits in its place at the edge of what is known as a precise and well-formed question, awaiting the development of the means to answer it. Europa has been circling Jupiter in its 3.5-day orbit for as long as Jupiter has had moons. The ocean beneath its ice, if it formed early in the moon's history, has been liquid for a time that is very difficult to set beside anything familiar. The age of that ocean, potentially measured in billions of years, is longer than the period of time during which complex multicellular life has existed on Earth. Whatever has been happening in that water has been happening for a duration that contains within it the entire history of animals, the entire history of plants, the entire history of vertebrates, the entire rise and diversification of life, from simple to complex, from ocean-dwelling to land-dwelling to airborne. All of that unfolded on Earth, while Europa's ocean simply persisted in its dark, in its cold, in its silence. The ice moves slowly over the surface above it. The tidal forces continue their patient work. The cracks open and close. The linear accumulate. The chaos terrain preserves the memory of past disruptions in frozen configurations. And somewhere below all of that, in a darkness that makes the midnight depths of Earth's deepest ocean seem well lit by comparison, the water moves in currents shaped by heat, rising from below, and the slow turning of the moon, carrying whatever it carries through an ocean that has been sealed from the outside world since before the first fish swam in Earth's ancient seas. Europa Clipper moves through the dark between the planets on a course that was calculated years before the spacecraft launched, refined continuously as it travels, its trajectory shaped by the gravity of every body it passes. When it reaches Jupiter and begins its series of flybys, each one will be an event planned in extraordinary detail, timed to the second, with every instrument configured for the specific geometry of that particular approach, and then the data will begin to return, transmitted across hundreds of millions of miles at the speed of light, arriving at antennas on Earth in a stream of numbers that will take teams of scientists years to fully interpret. Each piece of data from each flyby will contribute to a portrait of a world that has never been seen clearly. The portrait will be assembled slowly, with patience, one measurement placed alongside another over the course of the mission's years, until the outline of Europa's hidden interior begins to emerge from the data, the way a face emerges slowly from the developing surface of an old photograph, coming into definition from something that was barely there before. The spacecraft moves. The moon waits in its orbit. The ocean below the ice continues in its darkness. In the question that Europa carries, the most precise and carefully considered question about the nature of life in the universe that any generation of humans has yet been in a position to ask, remains open, unhurried, as patient as the ocean itself, waiting for the instruments to arrive, and for the slow and careful work of reading the answer to begin. Ganymede is larger than the planet Mercury. Hold that still for a moment. Not almost as large, not comparable in size. Larger by nearly 400 kilometers of diameter than a world that orbits the sun and bears the name of a Roman god, and has been classified a planet for as long as human beings have kept lists of such things. And yet Ganymede turns not around a star, but around a planet, one of 4 moons visible through a modest telescope on a clear night, one of 4 points of light that drift in their patient arcs and return again and again to roughly the same positions, steady and unhurried as they have been doing for 4 billion years. The diameter of Ganymede measures approximately 5,268 kilometers. Mercury's diameter is closer to 4,879. The gap between them is real, and it sits quietly at the center of what Ganymede is. Not a small thing, not a secondary thing, not a fragment or a captured remnant drifting in orbit by some accident of gravity, but a world of genuine planetary scale that happens to circle Jupiter rather than the Sun. It contains roughly 45% of Mercury's mass, because where Mercury is dense with iron and rock, Ganymede is composed in roughly equal parts of rock and water ice, and ice is lighter, two bodies of similar volume carrying very different weights, one a planet, one a moon. The distinction at this scale grows thin. Ganymede's surface, seen from a distance, divides itself into two broad territories, whose boundary is visible even from far away. Roughly a third of the surface is ancient dark terrain, brown and gray, and pocked so densely with craters that counting them becomes a way of reading time. These regions, called regions, carry the accumulated record of more than 4 billion years of impacts, every strike preserved in the ice, every crater a moment fixed in place, a collision that happened when the solar system was still arranging itself, when the planets were still sweeping their orbital paths clear of the debris left over from their own formation. The dark terrain of Ganymede is among the oldest exposed surface material in the solar system. It has not been resurfaced. It has not been overwritten by volcanism or folded by plate tectonics or washed away by rain or wind, because Ganymede has none of those things. What fell on it billions of years ago is still there, slightly softened by the slow and patient process of micrometeorite gardening, the constant faint rain of tiny particles that gradually churns and mixes the uppermost layer of any airless surface over deep time. But the craters remain. The history remains, written in ice and shadow. And then there is the younger terrain, covering roughly 2/3 of Ganymede's surface, brighter than the dark regions, and laced with a system of parallel ridges and long shallow troughs. The grooved terrain of Ganymede tells a different story. These ridges run for hundreds of kilometers at a time, curved in long, gentle arcs, their flanks catching sunlight at low angles and throwing long shadows. The boundary between the dark terrain and the grooved terrain is often sharp, in some places almost as clear as a line drawn with deliberate intention, and that sharpness is itself a record of something that happened here. What happened was extension. At some point in Ganymede's past, the icy crust was stretched, pulled slowly outward by forces rising from within. The older surface cracked and parted, and from those cracks, fresher material welled up, freezing quickly in the cold of space and spreading to fill the gaps. The process was not a single event, but a long episode, a period of geological renewal in which the crust fractured along many lines and was partially renewed, leaving behind those long grooves and ridges as the preserved record of where it opened and healed. Tectonics, the same broad class of process that built mountain ranges on Earth, worked itself out here in ice rather than rock, at temperatures far below anything that would feel like warmth to any living thing, and left its signature across most of a world. The boundary between the two terrains is a boundary between eras. On one side, the ancient, unmodified record. On the other, the reshaped, renewed surface of a moon that was once active enough to rearrange itself, both preserved, both readable, because nothing has come after to erase either one. At the southern pole of Ganymede, a bright impact scar marks a collision from the deep past, a large crater surrounded by radiating fractures and ejecta that spread across hundreds of kilometers. Craters like this are scattered across both terrain types, though more densely in the ancient dark regions than in the younger grooved terrain. Each crater has its own character. The largest ones, the ones that struck when the crust beneath was still warm enough to flow slowly in response to stress, have relaxed over time, their rims low and slumped, their interiors nearly level, the original sharp geometry of a fresh impact worn down to a gentle topographic remnant. These are called palimpsests, a word borrowed from the practice of scraping and reusing parchment, because in both cases the original content is still faintly legible beneath what came after. Smaller craters have retained their shape better, their rims are crisp. Their central peaks, the small mountains that form when the ground rebounds upward after a large impact's initial compression, are still visible, standing in the centers of circular basins, like the axis of something that happened in an instant and was then frozen in place for all the time that followed. The surface of Ganymede holds all of this in a kind of geological patience. It does not shift, it does not erupt, it does not pour material from one region to another the way a truly active body does, but it contains within it the record of the time when it did, or nearly did, and that record is deep. What lies beneath that surface is where Ganymede becomes something stranger and more layered still. At the very center, below many hundreds of kilometers of rock and ice, and compressed ice, in phases that do not exist on Earth's surface, there is a core. The best current picture, built from the measurements returned by spacecraft that have flown through this system, suggests that Ganymede's core is composed of iron, or perhaps iron mixed with sulfur, and that at least some portion of this core is liquid metal in slow, gradual convective motion, warmer material rising, cooler material descending, the whole interior turning in ponderous circulation, driven by the heat that remains from Ganymede's formation and from the slow decay of radioactive elements locked inside the rock. And from that convective motion in liquid iron, something emerges that no other moon in the solar system is known to produce. A magnetic field, not a field induced by an external influence, not a passive response to the changing magnetic environment of Jupiter nearby, but an intrinsic magnetic field generated from within, self-sustaining, the same category of field that Earth generates through the motion of its own liquid iron outer core. The mechanism is called a dynamo, and the result is a magnetosphere, a region of space around Ganymede carved out and defined by its own magnetic influence, embedded within the far larger magnetosphere of Jupiter, the way a small bubble sits inside a larger one. The scale of Ganymede's own magnetosphere is modest compared to Jupiter's enormous field, but it is real, and it is self-generated, and it makes Ganymede unique among all the moons of all the planets that have yet been studied. No other moon anywhere in the solar system is known to carry this property, to generate from deep within itself a magnetic field strong enough to define a region of space, to deflect incoming charged particles, to produce its own auroras. Those auroras were observed by the Hubble Space Telescope. In ultraviolet light, Ganymede glows faintly at its poles, two oval rings of luminescence, one near each magnetic pole, where charged particles spiral down the field lines and excite the sparse atmosphere above the surface into a faint emission. The atmosphere itself is thin beyond easy comparison. Oxygen, primarily, released slowly from Ganymede's icy surface by the action of charged particles from Jupiter's radiation environment, a process called sputtering. It is not an atmosphere in any sense that would shelter or sustain anything at the surface, but it is enough to glow, and the glow was observed and measured, and the measurement of how the glow moves carried within it an unexpected signal. The auroral ovals on Ganymede oscillate. As Jupiter rotates and its magnetic field rocks back and forth relative to Ganymede, the aurora ovals on Ganymede should shift their position in response, tilting one way and then the other as the external field changes. Precise prediction of how much they should shift can be made from what is known about Ganymede's own interior magnetic field. What the Hubble Space Telescope observed in 2015 was that the auroral ovals shifted by about 2 degrees from one side to the other, significantly less than would be expected if the only player were the magnetic interaction between Jupiter and Ganymede's solid interior. The discrepancy is small. It amounts to a few degrees of arc in the position of luminescent rings observed from more than 500 million kilometers away. But in that small discrepancy, carefully measured and carefully compared against careful predictions, was the signature of something hidden far below the surface. When a saltwater ocean is present beneath the moon's icy shell, it behaves as an electrically conductive layer. As Jupiter's magnetic field shifts and changes around it, that conductive layer generates its own magnetic response, an induced field that pushes back against the changing external field. On Ganymede, such an ocean would produce a secondary magnetic signal that partially cancels out the expected rocking of the auroral ovals, making them shift less than a purely solid interior would predict. The observed shift of roughly 2 degrees matched, within the uncertainties of the measurement, what would be expected if a saltwater ocean were present somewhere between about 150 and 800 kilometers below the surface. The ocean is not visible. It has never been directly sampled or imaged. Its existence is inferred from the behavior of light, from the motion of magnetic fields, from the careful comparison of observation against prediction. But the inference is strong, and it sits within the broader context of what is known about icy moons in the outer solar system, that the combination of tidal forces, internal heat, and the chemistry of water and salts creates conditions where oceans can persist in the deep dark for timescales measured in billions of years. On Ganymede, the ocean lies far deeper than on some of the other icy moons of Jupiter, hundreds of kilometers of ice press down above it. Below it, the pressure is high enough that the water sits on a layer of a different form of ice, high-pressure ice, that forms when water is compressed far beyond what Earth's oceans ever achieve. The ocean is sandwiched between ice above and ice below, sitting in darkness at pressures and temperatures quite unlike anything easily imagined, but persistent, stable, sustained by the slow warmth of radioactive decay in the rock beneath and by whatever heat the core releases upward through the deep interior. The water in that ocean has likely been there for a very long time. It does not cycle to the surface and back. It does not receive sunlight or material from outside. It is, in the best current understanding, an enclosed system, isolated, dark, and ancient. What Ganymede's interior presents, then, is a stack of distinct layers, each with its own character. From the surface downward, ice and exposed rock and ancient craters and grooved terrain, all the way down through the upper crust. Then a layer of warmer, softer ice. Then the ocean, hundreds of kilometers deep in places. Then high-pressure ice again. Then the rocky mantle. Then the core, iron-rich and partially liquid, turning slowly in convective motion and generating from that slow turning the magnetic field that reaches up through all the layers above it and defines a small magnetosphere in the space outside. In Earth's interior, these layers are sorted by density and heat into a recognizable sequence: inner core, outer core, mantle, crust. The sorting happened early, in the planet's first tens of millions of years, when Earth was hot enough throughout to allow dense material to sink and lighter material to float. This process is called differentiation. Ganymede differentiated. The rock and metal settled toward the center. The ice rose toward the outside. The layered interior that spacecraft measurements have gradually revealed is the result of that early sorting, of material finding its level under gravity when the whole body was warm enough to flow. Other moons have not fully differentiated, or have only partially done so, because they never reached the temperatures necessary. Ganymede did, and the result is a body with the internal complexity of a planet: core, mantle, ocean, crust, wearing the orbital classification of a moon. This complexity sits quietly in Jupiter's outer family of worlds, third in the sequence from the planet, between Europa at about 670,000 kilometers and Callisto at nearly 2 million. Ganymede orbits at roughly 1,070,000 kilometers from Jupiter's center, completing one full circuit in just over 7 days. It participates in the same orbital resonance that keeps Io and Europa in their precisely locked periods for every orbit Ganymede completes. Europa completes 2 and Io completes 4. The three bodies in a rhythm called the Laplace resonance that has shaped the thermal histories of all three worlds. For Io, the resonance means perpetual tidal flexing and volcanic heat. For Europa, it provides the warmth that keeps an ocean liquid beneath a cold ice shell. For Ganymede, the tidal effect is gentler. Ganymede is larger, and its orbit is farther from Jupiter, so the gravitational flexing is less intense than it is on the inner two. But some contribution from tidal heating may still reach into Ganymede's interior, adding a small increment of warmth to what radiogenic decay and core cooling already provide. The precise accounting of Ganymede's heat budget is not yet settled. The instruments that would measure it directly have not yet arrived. They are on their way. The European Space Agency launched a spacecraft called the Jupiter Icy Moons Explorer in April of 2023. It carries 10 scientific instruments, among them a radar sounder designed to penetrate the ice of Ganymede and return echoes from whatever lies beneath, a laser altimeter that will map the moon's surface to centimeter-level precision, and a high-precision magnetometer capable of resolving the fine structure of both Ganymede's intrinsic field and the induced signal of the ocean below. After a long journey through the inner solar system, using gravitational assistance from Earth, Venus, and Jupiter's own gravity to reshape its trajectory, the spacecraft will arrive in the Jovian system and spend several years studying multiple moons before doing something no spacecraft has done before in the history of space exploration. It will enter orbit around Ganymede, not a flyby, not a close approach. An orbit, a sustained trajectory, maintained for approximately 9 months, the spacecraft circling the largest moon in the solar system, as the moon itself circles Jupiter, carrying all of its instruments trained on the surface and the interior and the magnetosphere below, building up a picture of this world layer by layer in the slow accumulation of data that is how spacecraft science works. The radar pulses will travel downward through the ice and return upward with the faint echo of whatever they encounter. If there is an ocean at depth, and if the ice above it has the right properties for radar transmission, the echo of the ocean's upper surface should be distinguishable from the echoes of the ice layers above. The magnetometer will measure the induced field with a precision that exceeds what Galileo and Hubble together were able to provide, tightening the constraints on the ocean's depth and thickness and salinity. The altimeter will measure the tidal deformation of Ganymede's surface, the small but measurable flexing of the crust as Jupiter pulls on it from slightly different angles through the orbit, and from that deformation, the interior's mechanical properties can be inferred. 9 months in orbit, the spacecraft arriving in a place no spacecraft has orbited before, circling a world that is larger than Mercury and older than the oldest rocks on Earth's surface, sending its data home at the speed of light, which takes between 35 and 52 minutes to travel from Jupiter to Earth, depending on where the two planets are in their orbits. The image that settles the mind, sitting with Ganymede, is this: a pale sphere, larger than Mercury, its ancient dark terrain pocked with craters that record the first billion years of the solar system, its grooved terrain carrying the memory of a period when tectonic forces moved through the icy crust and left their geometry preserved in long curved ridges, its surface dusted with a thin mist of sputtered oxygen that glows faintly at the poles in ultraviolet light, the auroral ovals shifting back and forth by 2 degrees as Jupiter's enormous magnetic field rocks around them, each shift a little smaller than physics predicts for a solid body, the discrepancy pointing downward through hundreds of kilometers of layered ice and rock to a hidden ocean in the dark, and below that ocean an iron core turning slowly and generating from that slow motion a magnetic field that reaches up through all the layers and into the space above the surface, where it carves out a small magnetosphere of its own. All of this in a body that orbits another planet. The grooves on Ganymede's surface extend for hundreds of kilometers without break, running roughly parallel to one another in some regions, curving in broad arcs in others. They catch the low sunlight at the terminator, the line between day and night on the moon's surface, and become suddenly vivid, the long shadows making visible what flat overhead light would obscure. At that angle, the surface reads like a carefully scored material, line after line pressed into it during the period of extension, and then frozen in place for billions of years. Standing on the grooved terrain of Ganymede, if one could, the ground would be ice, cold, hard, gray-white ice mixed with rock and dust, with none of the blue translucence of glacier ice on Earth. The sky above would be black, even where the sun was visible, because Ganymede's atmosphere is far too thin to scatter sunlight into a blue arc the way Earth's does. Jupiter would dominate that sky, an enormous banded disk, the largest object visible, its cloud bands, pale orange and white and ochre, its great red spot, a warm-colored oval the size of Earth turning slowly in the upper atmosphere. Its brightness at this distance, roughly enough to cast a faint shadow on the ground. In the direction of Ganymede's orbital motion, the sky would show nothing unusual. The moon presents the same face to Jupiter at all times, tidally locked as the moon is to Earth, so Jupiter would hang at a fixed point in the sky, never rising, never setting, just there, always there, a constant presence above the horizon or overhead, depending on where one stood. The side of Ganymede that faces away from Jupiter would have a sky containing only stars, and the distant sun, smaller and dimmer at this distance than it appears from Earth, but still the brightest object in that direction by an enormous margin. And beneath all of that ice, without any warmth from that faint sun, without any warmth from Jupiter's light either, sustained by nothing the surface could offer, the ocean would be there, dark, still, old, at a depth that human engineering has not yet reached even on Earth. It would have been there for a long time. It will be there for a long time still. Its presence is felt, here in the slight and measured dimming of an auroral shift, in the careful accounting of magnetic fields, in the reasoning of scientists who have learned to read the interior of a distant world from the behavior of light and magnetism at its surface. Ganymede does not announce itself. It moves in its 7-day orbit without drama. Its volcanic interior, its differentiated interior, more precisely, the one that generated the heat necessary to produce all those layers, quieted long ago. The dynamo in the core persists, but more slowly now, the inner engine of the moon, running on the long-stored heat of formation and the patient decay of radioactive elements, dimmer than it once was, but still turning, still generating that magnetic field that makes Ganymede unique among all the moons of the solar system. There is something in the character of this moon that rewards stillness. The surface craters, worn and sharp, and ancient and fresh in varying degrees, record time in a way that does not require interpretation. Each crater is a fact, a specific impact, a specific moment, preserved without alteration in the ice. The grooved terrain records the episode of extension and renewal, the period when Ganymede's interior was warm enough to shape its own surface, and then cooled enough to preserve that shaping forever. The ocean below records the persistence of liquid water far from any sun, sustained by internal processes, a reminder that the conditions life requires, or at least some of them, are not exclusive to the sunlit regions of the solar system. And the magnetic field records the motion of liquid metal in a core, the same motion that generates Earth's own field, the same physics operating in a body orbiting another planet 5 times farther from the sun than Earth is. The physics does not know or care whether the body carrying it is called a planet or a moon. It works where the conditions allow it to work. On Ganymede, the conditions allow it. The auroral ovals near Ganymede's poles are perhaps the most quietly extraordinary of all of this. They glow in ultraviolet, invisible to any eye, visible only to the instruments of a space telescope pointed in the right direction from several 100,000 kilometers away. They are rings, roughly circular, surrounding the magnetic poles rather than the geographic poles, because it is the magnetic field lines that funnel the incoming particles and produce the light. They shift as Jupiter's field rocks back and forth. They shifted by 2 degrees when they were measured, and that 2 degrees compared against the 3 degrees that would have been expected told the people who measured it that something below the surface was generating a magnetic signal in opposition to Jupiter's field, and that something was most likely a saltwater ocean, 2 degrees of arc, hundreds of kilometers of ice, an ocean measured through the behavior of light. The patience required to work this out from first principles, to design the observation, to point the telescope, to process the data, to compare the measurement to the prediction, to identify the discrepancy, to trace the discrepancy to its cause. All of this happened incrementally, over years, carried out by people whose careers were long and whose results built on the results of others before them. The aurora moved 2 degrees instead of 3. The rest followed from that. When the spacecraft arrives at Ganymede and settles into its orbit, it will not be making a sudden discovery in the way that the first observation of something entirely unexpected tends to. It will be confirming and measuring and deepening what is already known, filling in the picture with finer detail, placing constraints on what the ocean's depth might be, refining the shape of the interior, measuring the tidal deformation of the crust to 3 decimal places. This is what sustained orbital science does. It takes a world that inference and flyby observation have sketched in broad strokes and begins to render it in finer and finer resolution, the picture clarifying slowly over 9 months of orbit, thousands of individual measurements, terabytes of data traveling home at the speed of light. The radar will send its pulses downward into the ice, and the pulses will return, and from the timing and the shape of the return signal, the structure of the ice beneath will become legible in a way it has never been before. The magnetometer will measure the field at many positions through the orbit, building up a three-dimensional map of how the field varies across Ganymede's magnetic environment. The altimeter will ping the surface thousands of times per orbit, accumulating a topographic map of such precision that the small tidal deformation of the crust, the slight rise and fall of the icy surface as Jupiter's gravity pulls on it from varying angles, will be measurable in the data. From the tidal deformation, the interior's elastic properties can be calculated. An ocean, being liquid, allows more deformation than a fully solid interior would. The expected deformation for a moon with an ocean is different from that of a moon without one. The measurement will sharpen the inference. It will not resolve every question. There are always deeper questions, and the best measurements tend to produce new ones, but it will narrow the range of what is possible, and in that narrowing, the picture of what Ganymede actually is will come closer to what Ganymede actually is. 9 months in orbit. For most of Earth's history, the concept of sending a machine to circle a moon of Jupiter and listen for the echo of an ocean beneath its ice was beyond any framework of human thought. The telescope that first identified Ganymede as a specific body, distinct from a star, was held in human hands in a cold room in Padua, and the person holding it could not have seen it clearly enough through the optics of the time to distinguish any feature on its surface. It was a point of light. It moved. That was the observation. 4 centuries of accumulated understanding separate that point of light from the layered world it points toward, a world with a differentiated interior, a dynamo-generated magnetic field, a tectonic history preserved in grooved terrain, a hidden ocean inferred from the behavior of auroral light, and a spacecraft on its way to spend 9 months in orbit, measuring all of it as carefully as the instruments allow. Ganymede's auroral belts shift and glow at its poles in light no eye can see, generated by particles guided down magnetic field lines that rise from a liquid iron core, turning slowly in the deep interior of the largest moon in the solar system, a moon larger than a planet, holding its orbit around Jupiter with the same steady patience it has held for 4 billion years. While far above its ancient cratered surface, in the ultraviolet quiet of its polar regions, the faint rings of aurora oscillate their 2 degrees and wait without impatience for whatever comes next. Each crater on Callisto's surface is a number, not a symbol of one, not a loose metaphor for time, an actual count, pressed into the ice and rock of an entire world, accumulated over roughly 4 billion years of patient collisions in the dark, where other moons have been reshaped by heat and tide, where surfaces have cracked and flowed and been remade in the intervening years. Callisto has simply received. It held still, and what fell on it stayed. The surface that exists today is very nearly the surface that formed when the solar system was young and crowded with debris, when the space between the planets was still being slowly cleared, and the record of that long clearing is written on this moon in the only language it has ever spoken, the deep, quiet language of craters. There are places on Callisto where new craters sit inside older ones, and older ones inside older still. The layers compound each other like rings inside a tree, though these rings are not years, but eons, individual moments of impact stacked so densely that it becomes difficult, from orbit, to find a single patch of ground that has not been struck at least once. The older craters are soft at the edges. Billions of years of tiny impacts, grains and particles too small to leave their own marks, have worked at the rims of the ancient basins and slowly rounded them, slowly settled the walls inward, worn the sharpness out of them the way wind wears the edge of a stone. Nothing dramatic erases them, only the slow persistence of small things, over time that has no name for how large it is. Callisto orbits Jupiter at a distance of roughly 1,880,000 kilometers. It takes just under 17 days to complete one orbit, moving at a steady, unhurried pace far outside the inner three moons. At that distance, the sky above its surface would show Jupiter as an enormous presence, not a point of light as a planet appears from Earth, but a vast banded disk, pale and striated, the cloud belts visible with the naked eye, the great red spot, a faint smear depending on where, in its own rotation, Jupiter happened to be. The planet would dominate roughly 6 degrees of the sky. Nothing else in that sky would come close to it. The sun would be a very bright star, small and distant, casting faint shadows across the cratered ground, illuminating the ice with a cold, diffuse light, very unlike the warm flood of it on Earth. The surface beneath that sky is dark. Callisto is one of the darkest large objects in the solar system, reflecting only about 20% of the sunlight that falls on it. The material on the surface, rock and ice worked over by 4 billion years of micrometeorite impacts, darkened by irradiation, coated by material delivered from elsewhere, absorbs most of the light that reaches it. Standing on Callisto, if standing were possible, the ground would look something like very old, dark stone, not the bright white of fresh ice, not the color of the moon's highlands, but something closer to the gray-brown of ancient weathered terrain, softened at every edge, flat in a way that speaks not of smoothness, but of immense age, worn level. In the northern reaches of Callisto's surface, there is a structure so large it reads at first less like a feature and more like a region. It is called Valhalla, and at its center lies a bright plain, roughly 600 kilometers across, a pale disk of lighter material marking the place where something large and fast arrived, a very long time ago. That plain is surrounded by rings, not shallow rings, not subtle variations in terrain, but concentric ridges and scarps spreading outward from the impact point in every direction, extending to a total diameter of nearly 4,000 kilometers. The outermost rings are nearly 2,000 kilometers from the center. They are the frozen memory of a wave that passed through the surface of this moon when the impactor struck, when the crust beneath was warmer and more yielding than it is today, and the material responded less like solid rock and more like something between stone and water. The wave traveled outward. It reached a certain distance, and then the crust cooled enough that the wave stopped there, mid-motion, preserved in place like a photograph of a moment that has not changed since. The impact that made Valhalla would have been one of the largest events Callisto experienced in its long history. The scale of the concentric rings makes it possible to infer roughly how yielding the crust was at the time, and the ring's extent implies a surface that had not yet fully hardened, a moon still early in its cooling, the interior still holding enough warmth to let the crust deform in that characteristic spreading pattern. In basins on other worlds where the crust was already rigid, the rings are fewer, closer together, steeper. On Callisto at the time of Valhalla, the ground gave and gave and gave, and the rings record exactly how far that giving went before it stopped. They have been there, counting nothing, since. The interior of Callisto is unusual in a way that speaks to its entire history. Most large bodies in the solar system that formed with a mix of rock and ice, and Callisto is roughly half rock and half ice by composition, went through a process called differentiation, in which the interior heated enough that the denser material sank toward the center and the lighter material floated outward, creating distinct layers, a core, a mantle, a crust. This is how Ganymede is built. This is how the rocky planets are built. But Callisto, at least in the best current understanding, never fully differentiated. The rock and ice inside it appear to be mixed, compressed together, settled under gravity, but not sorted into clean separate layers the way heat-driven separation would produce. The leading picture is of a body that formed and then simply cooled, without ever generating the internal heat that would have driven the sorting process. No tidal flexing reshaped it. No resonance with other moons pumped energy into it. It formed in the outer part of the Jovian system, accumulated its mass, and cooled, and what is inside it today is very close to what was inside it when it was young. That makes Callisto a kind of record in itself. The surface records the early solar system's bombardment. The interior, undifferentiated and largely unchanged, carries within it the composition of the material from which it formed, the ratio of rock to ice, the mix of compounds that were present in the outer Jovian disk 4 billion years ago. There is something very still about a body that has remained so close to its original state for so long, not frozen in a dramatic sense, not a violent freezing, not a sudden stop, but a slow, patient, almost effortless persistence. The rest of the solar system went on changing. Callisto held its shape and held its record, and did not need to explain itself. There is, however, one thing about Callisto's interior that does not quite fit the picture of total inactivity. When the Galileo spacecraft passed close to Callisto in the 1990s, its magnetometer detected a faint but consistent magnetic response, not an intrinsic field like the one generated by Ganymede's iron core, but an induced one. Something inside Callisto was responding to the changing pull of Jupiter's vast magnetic field, shifting slightly as that field moved, in the way that electrically conductive material responds to a changing magnetic environment. The best current explanation is that somewhere deep inside Callisto, there may be a layer of liquid, a saltwater ocean, possibly kept from freezing, not by internal heat, but by compounds in the water that lower its freezing point, ammonia among them, pressing down the temperature at which water becomes ice. The ocean, if it is there, would be deep, perhaps 150 kilometers down, perhaps much deeper. It would be cold, far colder than Europa's ocean, sitting in a body with very little heat to spare. But the signal in the data is real, and the inference made carefully, framed with the honest uncertainty it deserves, is that Callisto may hold water in liquid form simply by virtue of its composition rather than its warmth. The ocean is not confirmed in the way Europa's is. The magnetic signal can be explained in other ways, and there is no secondary evidence from surface features, no linea, no chaos terrain, no signs of material exchange between an ocean and a crust to support the inference. The best that can be said is that the signal exists, that a saltwater ocean is consistent with it, and that the question is genuinely open. Callisto keeps its interior hidden behind its ancient cratered face, and offers only this one faint magnetic whisper as a clue to what might lie beneath. That whisper is enough to hold the question alive, calmly, without urgency, without the need to resolve it before it is time. What is known with more confidence is the radiation environment at Callisto's distance from Jupiter. The Jovian magnetosphere is a vast and energetic structure, a region of space where charged particles are trapped and accelerated by Jupiter's magnetic field, forming belts of radiation that would be dangerous to human biology and to unshielded spacecraft electronics. The inner moons sit well within these belts. Callisto, at its greater distance, sits largely outside the most intense regions, in a part of the magnetosphere where radiation levels are far lower. Not zero, Callisto is still inside Jupiter's system, but manageable enough that spacecraft visiting Callisto require less shielding than those visiting the inner moons, and enough that serious scientific proposals have considered Callisto as a potential location for human operations in the Jovian system. The ice in Callisto's surface is another part of that calculation. Water ice, processed with enough energy, yields oxygen and hydrogen. The same ice that forms the bulk of Callisto's composition could, in principle, be extracted, separated, and converted into water for crew support, into oxygen for breathing, into hydrogen and oxygen as propellant. This is the concept known as in situ resource utilization, using the materials already present in a place to support operations there, rather than carrying everything from Earth at enormous cost. Callisto's ice, its relatively low radiation environment, its stable and undramatic surface, its position within the Jovian system, close enough to visit the other moons, while far enough from the planet to be manageable, these things together have made it the subject of genuine interest in long-range mission planning. Not imminent planning, not near-future planning, but the kind of careful, thoughtful planning that a species with curiosity and patience performs when it begins to think seriously about the places it might one day go. There is a particular quality to imagining a human presence at Callisto, not the urgency of a destination, not the glamour of a dramatic world, no plumes rising into vacuum, no ice laced with the possibility of ancient organisms, no magnetic auroras pulsing at the poles. Just a very old, very dark, very quiet world, its surface covered in craters, Jupiter enormous in the sky above, the sun a small and distant light, the ice beneath the surface holding water that has been compressed and kept for 4 billion years, waiting for nothing, expecting nothing, simply there. There is something almost restful in that image, a world that does not perform, a world that has nothing to prove. The 4 moons of Jupiter were found within a few weeks of each other, in the cold of a single winter. They were recorded as points of light, moving in relation to a bright planet, noted in ink on paper in a sequence of sketches that tracked their positions night after night. They were named, they were studied from the ground for centuries, their orbits measured with increasing precision, their sizes estimated, their surfaces imagined, and then, in the 20th century, spacecraft arrived. Io was reached first, and what the first close images showed was a surface unlike anything predicted, yellow and orange and black and white, sulfur in every state, no craters at all, because the volcanic activity had buried every one under fresh material. The volcanoes were active as the spacecraft flew past. A plume was discovered in a navigation image, rising more than 300 kilometers above the surface, arcing outward in total silence into the vacuum. The interior of this moon, kneaded continuously by Jupiter's gravity, working through the slight elongation of its orbit, generates enough heat to keep a portion of its mantle partially molten, to drive lava across the surface in vast, slow floods, to create lava lakes larger than some of Earth's countries. The volcanism on Io is not explosive in the terrestrial sense, not sudden, not violent in the way a human mind reaches for when it hears the word volcano, but continuous, persistent, welling up steadily from an interior that is never fully at rest. The heat comes not from radioactive decay, not from the original warmth of formation, but from the ongoing tidal friction of Jupiter's pull, working against the slight back and forth of Io's elliptical path, squeezing and releasing the rock with every orbit the way a hand might slowly work a piece of dense clay, generating warmth through nothing more than the persistence of that motion over time. And Io's relationship to Jupiter does not end with heat. As the moon moves through Jupiter's magnetic field at enormous speed, it acts as a natural generator, a conductor moving through field lines. inducing a current. That current flows along the field lines connecting Io to Jupiter's polar regions, arriving at the planet as a faint shimmer of auroral light, a signature visible in ultraviolet, evidence of the electrical conversation between a moon and its planet, carried out silently in the cold of space. Material from Io's volcanoes, sulfur dioxide, sulfur, oxygen, escapes into space and becomes ionized in Jupiter's magnetosphere, swept around the planet in a broad torus of glowing plasma that traces the path of Io's orbit. The volcanic heat of one small moon becomes, in the end, part of the structure of the entire Jovian magnetic environment, everything connected to everything else in slow, patient, invisible ways. Europa is smooth, where Io is mottled, pale where Io is vivid, and quiet at the surface where Io is perpetually active beneath it. But beneath Europa's ice, there is something that may be larger and stranger than all of Io's volcanism. The ice shell of Europa, a layer that may be as thin as a few kilometers in some places and perhaps as thick as 30 in others, rests on top of a global ocean of liquid water. The inference comes from magnetic data, from the way Europa responds to Jupiter's changing field, from the conductivity implied by that response, which is consistent with a deep layer of salt water extending all the way around the moon. The ocean is estimated to hold roughly twice the volume of all of Earth's oceans combined. It has been liquid, in the best current picture, for a very long time, kept from freezing, not by sunlight, which barely reaches this far, but by the same tidal friction that heats Io, the same orbital resonance that keeps Europa's path slightly elliptical, the same patient compression and release of an interior caught between Jupiter's pull and the rhythmic nudge of neighboring moons. The surface of Europa shows the history of that tidal stress written plainly across the ice. Long brown lines cross and recross the white surface. Linea, they are called. Ridges and bands formed when the ice cracked under the tension of tidal flexing, and the gap filled with fresh material from below and refroze. There are places where the ice appears to have broken into large plates that shifted out of their original positions and then refroze in new configurations, the pattern resembling a puzzle whose pieces have been gently rearranged. The surface is young, in geological terms, only about 40 to 90 million years old, estimated from the relatively low density of impact craters, which implies that whatever lies beneath the ice is still actively renewing it, still delivering fresh material to the surface, still working. The ocean is not sealed off from the ice above it. There is exchange in both directions over geological time. The significance of a global saltwater ocean, warmed from below by tidal heating, existing in permanent darkness, far from the sun, is that it expands what is meant by the word habitable. On Earth, the concept of a habitable zone is built around distance from a star, the band of distances within which liquid water can exist on a planetary surface. Europa lies far outside that zone, yet it has liquid water in abundance, and a persistent source of internal energy, and a rocky seafloor over which that water moves. The conditions that might support life, under the current understanding of what life requires, do not depend on sunlight. They depend on liquid water, on energy, on chemistry, and Europa has all three. What it does not have yet is any direct evidence of biology. No organism has been detected, no biosignature has been confirmed, no sample has been returned. The question remains genuinely open, and it will take instruments far more capable than any so far deployed to begin to answer it. But the conditions are there, the ocean is there, and the question carefully framed and honestly held is one of the most significant in planetary science. Ganymede is the largest of the four, larger in diameter than the planet Mercury by nearly 400 kilometers. Mercury is a planet orbiting the Sun, and Ganymede is a moon orbiting Jupiter, and yet Ganymede is bigger. The comparison sits quietly once it is made, rearranging something in the way scale is held in mind. The size does not mean Ganymede is the more massive of the two. Mercury is denser, more rock and metal, while Ganymede is roughly half ice and half rock, which means Mercury contains more mass in a smaller body. But in terms of diameter, in terms of the space Ganymede occupies, it is the larger object. It is a planetary scale world that the solar system happens to have placed in orbit around another planet. What makes Ganymede unique among all the moons known in the solar system is its magnetic field, not an induced field like the one inferred from Europa's or Callisto's magnetic signatures, but an intrinsic field generated from within, arising from the slow convective motion of a liquid iron or iron sulfide core deep inside the moon. The same process that generates Earth's magnetic field, the same slow churning of molten metal driven by the heat of the planet's interior, operates inside Ganymede, in miniature, producing a genuine magnetosphere, a region of space around the moon where the magnetic field is Ganymede's own, carved out within the much larger magnetosphere of Jupiter. The Hubble Space Telescope observed auroras on Ganymede, rings of ultraviolet light near the poles, produced when charged particles follow the moon's own magnetic field lines down into its atmosphere and collide with gas. The auroras shift back and forth slightly in response to changes in Jupiter's broader magnetic environment, rocking gently like a compass needle responding to a nearby magnet. The precise measurement of how much they shift compared to how much they would shift if there were no other conductor interfering revealed that something inside Ganymede is generating an opposing magnetic signal, something large, something electrically conductive, something deep. The best current picture places a saltwater ocean between roughly 150 and 800 kilometers below the surface, sandwiched between layers of ice too deep for any surface feature to show its presence, visible only through the faint rocking of the moon's aurora under Jupiter's magnetic influence. The surface of Ganymede carries two distinct landscapes in roughly equal portions. One is dark, ancient, heavily cratered terrain, some of the oldest surface in the solar system, dating back more than 4 billion years, a record of the early bombardment preserved in dark material of uncertain composition. The other is bright, grooved terrain, marked by long parallel ridges and troughs running for hundreds of kilometers, evidence that the icy crust was stretched and fractured and partially renewed at some point in Ganymede's past, when the interior was warm enough to allow that kind of tectonic activity. The boundary between the two types of terrain is often sharp, an abrupt transition from the heavily cratered ancient ground to the younger grooved surface, as clear as a visible line drawn between two geological eras separated by hundreds of millions of years. Inside Ganymede, the layers are distinct in the way Callisto's are not. A liquid iron core at the center, in slow convective motion, a rocky mantle above it, then ice, compressed under the weight of the material above, perhaps in exotic high-pressure crystalline forms, unlike the ice of a winter lake, and then the ocean, and then more ice, and finally the surface. The internal heat that drives the dynamo, that kept the differentiation process running long enough to sort the interior into these distinct layers, comes partly from the residual heat of Ganymede's formation, and partly from the decay of radioactive elements in the rocky portion of the moon. Tidal heating plays a smaller role here than it does in Io or Europa. Ganymede is in orbital resonance with the other two, but its particular place in that resonance produces less tidal flexing than theirs. The heat inside Ganymede is older, quieter, slowly diminishing, a warmth held over from the beginning of the moon's history, still enough to sustain the dynamo for now, but not forever. There is a spacecraft on its way to Ganymede. It was launched in April of 2023, and it will not arrive in the Jovian system for several years yet. When it does, it will conduct a series of flybys of all 3 icy moons before entering orbit around Ganymede in 2034, the first spacecraft ever to orbit a moon other than Earth's own. It will spend 9 months in that orbit, measuring Ganymede's magnetic field with precision instruments, sounding through the ice with radar, mapping the surface in detail, and returning data about this moon's interior that no ground-based observation or distant flyby can provide. 9 months of patient, careful measurement in orbit around the largest moon in the solar system, gathering the numbers that will eventually allow scientists to say with confidence how thick the ice is, how deep the ocean sits, how strong the dynamo still burns. The data will come back slowly, over months and years, and the picture will assemble itself piece by piece, and there will be no single dramatic revelation, only the gradual accumulation of detail. That is how science works at its best, patient and precise, and free of hurry. Callisto sits at the edge of all of this. It sits at the edge of the resonance. Outside it, technically, its orbit too wide and too slow to lock into the rhythm that drives tidal heating in the inner 3. It has no active volcanism, no confirmed subsurface ocean, no intrinsic magnetic field. Its surface has not been remade in 4 billion years. It simply orbits, steady and dark, and covered in the record of everything that fell on it, when the solar system was young, holding its shape without effort, without the constant internal renegotiation that keeps the other 3 in perpetual geological conversation with Jupiter's gravity. There is a quality to Callisto that is almost like stillness achieved. Not a stillness that was imposed, but one that was simply arrived at, the stillness of a very old thing that has long since finished becoming what it is. These 4 worlds were found together in a matter of weeks by a man looking at a bright point of light through a long, narrow tube in a cold winter sky. They appeared as points of light beside that brightness, arranged in a nearly straight line, their positions shifting from one night to the next in the careful, precise way that orbiting objects shift, not drifting randomly, not fixed like background stars, but moving in a pattern that repeated itself, that could be predicted, that followed rules. The rules were the same rules that held the moon in orbit around the Earth. The discovery that those rules applied to objects orbiting something other than Earth changed the model of how the cosmos was organized, calmly and irreversibly, like a key turned in a lock. 400 years have passed since those first sketches were made. In that time, the points of light have become worlds with surfaces and interiors and magnetic fields and oceans. The instruments sent to them have been small and distant, and then closer, and then orbiting, and then eventually hovering within kilometers of their surfaces, close enough to photograph individual features that are smaller than a city block. Each wave of exploration has revealed something that the previous wave could not have imagined, and each new detail has settled into a larger picture without resolving the whole, because the picture keeps growing. There is always more interior than the instruments have reached. There is always more depth than the radar has sounded. There is always a layer beneath the layer that has been measured, waiting for the next generation of instruments to speak to it. Jupiter itself has been there through all of it, 4 billion years before any instrument measured it, before any eye observed it, before any mind named it. It was already there, already enormous, already banded, already holding these four worlds in orbit as they accumulated from the disk of material that surrounded the young sun. The orbital resonance that drives the volcanism of Io and the ocean of Europa was already established within the first few 100 million years of the solar system's history. Callisto was already collecting impacts. Ganymede was already differentiated, its iron core already generating the magnetic field that would one day cause auroras to shimmer at its poles. All of this was already in motion before there was anyone to notice it, before there was any Earth complex enough to produce a living thing, before there was anything in the solar system that looked at the sky and wondered what was in it. And then, eventually, there was. And the wondering has not stopped since. The four moons hold their positions around Jupiter now, as they have always held them, in the steady circular dance of orbital mechanics, each at its particular distance, each at its particular pace. Io completes an orbit in less than 2 Earth days, moving so fast through Jupiter's magnetic field that the electrical current it generates is continuous. The plasma torus it feeds is continuously replenished. The lava on its surface is continuously renewed. Europa takes just under 3.5 days, its tidal flexing steady and persistent, the ice above its ocean cracking and healing in slow rhythm with the orbit. Ganymede takes just over 7 days, its massive bulk moving with a solemnity appropriate to the largest moon in the solar system, its magnetic field steady and quiet, its auroras rocking gently at the poles. And Callisto takes just under 17, the slowest of the four, the farthest out, unhurried in the dark at the edge of the inner system, its cratered face turned toward Jupiter, its ancient interior resting in the long stillness of something that formed and then was done forming. They are visible from Earth on a clear night, with binoculars, as 4 small points of light arranged along Jupiter's equatorial plane. Not as worlds, not as volcanoes and oceans and magnetic fields and ancient craters, just as 4 faint spots beside a bright one in the black between the other stars. But the 4 faint spots are moving if the observation is repeated the following night and the night after and tracked with patience. The positions will have shifted. The pattern of their motion will reveal the same rules that were written down 4 centuries ago by a man in a cold room in Padua who looked at them and understood, slowly, what they meant. The light leaving Jupiter tonight takes roughly 40 minutes to reach the Earth, give or take depending on where the 2 planets are in their orbits. By the time it arrives, it carries within it the faint reflected gleam of 4 worlds, one burning, one hiding an ocean beneath its ice, one generating its own magnetic field from a molten iron core, one holding the memory of 4 billion years in its craters. The light does not know what it carries. It travels because light travels, and it arrives because that is what light does across the distances of space, indifferent to the complexity it has passed. Jupiter sits in the sky on any given night. If the sky is clear and dark, large enough to be obviously a disk, through a modest telescope, its bands visible, its moons strung out beside it like a sentence in a language that takes a long time to read. The planet has been there longer than the Earth has been solid. It will be there long after tonight's darkness passes and the light comes again.